Okay, today is day 20, lesson 20 for the course. Today we finally get to use the term derivative, which I've kind of already used because it's hard for me not to use it. But this thing we're calling the slope of the tangent line is in fact a derivative, and now we can officially call it that. This instantaneous rate of change is a derivative. Now we can officially call it that. Just as we go through this and we begin to get some different techniques for finding derivative, a product rule and a quotient rule and a chain rule and implicit differentiation, I'll try to not let you lose sight of the fact that this thing is in reality a slope or an instantaneous rate of change. I think sometimes we kind of get caught up in the algorithms that help us find derivatives, but let's keep in mind what it is. It's a slope of a tangent line to a curve, or an instantaneous rate of change. So the first thing that you'll see highlighted in your book is this definition. Number 2, if the right side of that looks very familiar, that's exactly what we worked with last time we were together. So if that looks like the slope as it was stated in the book, or as I have stated, the slope of the tangent, then you're remembering that correctly, that is what we call the slope, or the slope of a curve, or the slope of the tangent line to the curve, and now we give it a new name saying it's the derivative of the function. So this notation, this f prime of a, I think prime probably came from the fact that another term in the history of calculus used to be used for derivative. It was called a primitive. So possibly the prime came from it used to be called a primitive of the function. But that's the derivative of the function f at the specific number a, or f prime of a. So it's nothing more than what we've already done. It's the slope of a curve, or the slope of the tangent line to the curve. Now, since we also had this as the slope, or the slope of the tangent, then that's an alternative definition for the derivative of a function at a certain value. Now, which one do you use and when do you use it? I would probably choose this one most of the time because we're handed the function. It's easy to put in a plus h for the variable, and just as easy or easier to put in a for the variable. This can be used, but a lot of times it requires a little bit more complicated algebra in the simplification. So I would say, when in doubt, choose this first definition, and then occasionally, especially if they kind of hand us that or tell us to use that, then we'll use that secondary definition. They both mean the same thing. What they are is the slope of a secant line where you've got 2 points, and then each of them in their own way lets the 2 points get closer and closer together. So for all practical purposes, you have 1 point. And that's what a slope of a tangent is, the slope at a certain point. So an example, let's find the derivative. Let's find the f prime at a for this function, 2x squared minus 9x plus 11. So we know what that is. We know it's a parabola. We know the parabola opens up, and we know it's a little skinnier than the normal y equals x squared parabola because of the 2 in front of the x squared. So if we want the f prime of a, the derivative of this function at some specific a value that we choose later, then we want, by definition, so if we say definition of derivative, this is what we're talking about. Now there are some shortcuts that we're going to be learning, but if we say find the derivative by the definition of derivative, this is the thing we need to use. So what is the function at a plus h that says to put in an a plus h everywhere you see the letter, which in this case is x. So instead of 2x squared, it's 2a plus h squared. Instead of minus 9x, it's minus 9a plus h. And then plus 11 doesn't have a variable in it anyway, so we just bring that along. So that's the function at a plus h minus the function at a. Everywhere you see an x, replace it with an a. And all of that is going to be divided by h. Look familiar? Kind of the same stuff we've been doing here for the last couple days anyway. So a plus h, the quantity squared, is a squared plus 2ah plus h squared. We got minus 9a minus 9h plus 11. Everything that follows gets subtracted, so we're going to subtract 2a squared. Going to subtract a negative 9a, and we're going to subtract 11. So that's still all divided by h. And let's distribute. Try to get one more line here. Two a squared plus 4ah plus 2h squared. And all of that's going to be divided by h. Is that all right? Any arithmetic mistakes on my part? I hope not. Did we lose anything at this point in time?
2a squared.
2a squared minus itself. What else?
11.
Minus 9a plus 9a plus 11 minus 11. And not by coincidence, it is true at this point in time that everything left in the numerator has what in common?
H.
Has an h. Okay? So let's factor an h out. It's in there 4a times. It's in there 2h times. It's in there minus 9 times. That's it, right? Now, what's the advantage of having factored an h out of the numerator? Okay, we can reduce h over h. When can we not reduce h over h?
If it equals 0.
When h is 0, but h is not exactly 0. It's approaching 0, so we're okay. And now we have the limit, as h is getting very close to 0, of 4a plus 2h minus 9. What happens to that stuff as h approaches 0? Okay, we lose this term because h is getting smaller, so that term disappears, so it looks like we've got 4a minus 9. Is that okay? Some of you know the shortcut. Look at the original function. There's the original function. Does that, if you know the shortcut for finding a derivative, does that seem to be correct? How many of you know the shortcut? 1, 2, 3, 4, 5. 5 of you? We'll have to trust those 5 people right now. Don't trust me. You know better than that. But we'll trust them that that is, in fact, the derivative. So that's the derivative at a. Well, what is the derivative at a? It's the slope of the tangent line at any value a, comma, f of a. So that's what we just found. The slope of the tangent to that curve at some given x value, we'll just call it a. So it has a variable slope. Is that right? So as we are at different points on the curve, the slope is different. Make sense, right? Parabola. It's not the same slope all the time. If it's the same slope all the time, it's not a parabola. What is it? What has constant slope? A line, right? So a line, regardless of where you are, has the same slope. That's what makes it a line. This is a parabola, so it has variable slope, and that slope is found by multiplying the x value by 4 and subtracting 9. Is that okay? A little algebra to the problem, and what we get then is called a derivative. Okay, the next issue that the authors of your text take up is that of the fact that this derivative is this. Okay, and I think I've already basically kind of gone ahead to that. It's hard for me to separate these things because I've kind of learned them all together, and it's hard to talk about the slope of the tangent without talking also about the instantaneous rate of change, without also talking about the derivative. So that's why it's hard for me to separate them. But the next topic taken by your authors, the tangent line to some curve y equals f of x at some point a comma f of a is the line through the point whose slope is equal to the f prime of a. So what is the f prime of a? It's the slope of the tangent line. So it's a derivative, but it also has some meaning rooted in how we defined it. So what that allows us to do, let's say we wanted the equation, and we're going to do this on an example, but let's just do this piece right here. The equation of the tangent line at a certain point. Well, we've used this before. Now we would plug in the coordinates of the point. So the point is a comma f of a. And what do we know to be the slope of the tangent to the curve according to that particular statement? F prime of a is correct. There's the slope of the tangent. So that goes in that position. So we've done problems where we've found the equation of the tangent line. So this would give us kind of a starting point. If we can start right here, then we can basically just sub in to our final answer. Plug in the derivative for the slope, plug in the a for the specific x value, the f of a for the specific y value, and then we're ready to go with that. Okay, an question?
So what we just did, the first example, that would be an instantaneous rate of change?
It is that.
All right.
It's all of those things. It's the slope of the tangent, it's the derivative at a, and it's the instantaneous rate of change at a. So all three of those, if you can kind of put those all in the same basket, they're all equivalent. In fact, let's go back to that first example and add to the problem. Let's say we want to find the equation of the line that is tangent to this function. That function ought to look familiar. That's the one we just used, I hope. That's what I want to do anyway. At the point -1, comma 22. So y minus the known y value is slope x minus the known x value. And what's the slope of the tangent line? Which is kind of a giveaway, right? Based on how I just asked the question. What's the slope of the tangent line? It's the derivative at a, which we just did, so we don't have to do that again. What did we get for an answer? 4a minus 9. Now, do we know A in this problem? Do we know the specific x value that we want to know the slope? Yeah, we do. We want to know the slope at -1. So we plug in the specific x value that we're handed in the problem, the point of tangency, the x value of the point of tangency, and then we know how to find the derivative, the slope of the tangent. It's 4a minus 9. What do we get for the slope?
Negative 13.
-13. Now we could solve that for y and put it in y equals mx plus b form or some other form. Once again, if you get to this point in this problem, you can stop because I know that you know what you're doing. Yeah, which is fine. Putting it in another form is fine, but we can just leave it here is fine also. So what's the important part of that problem? This piece is that once we find the derivative, that is the slope of the tangent line to the curve.
Are we
That
going to
okay?
go over the shortcut?
Not today.
All right.
And this has some merit because I think it does, even though it is a little frustrating that we're having to go through this whole limit process and do all the algebra. I agree with you. It is, after a while, it becomes a little frustrating. But it does serve a purpose because it does clearly show. Let me go back to this problem we just did. I know when I look at this problem, especially when I look at this part of the problem right here, that reminds me that this thing is really a slope. It looks like to me the difference of two y values, and then I know that in the bottom, h is the difference of the two x values. So that reminds me that this is a slope, and that's kind of what the purpose of it is to define it in terms of a limit, the limit of the slope of the secant as the 2 points approach the same point. All right, let's, we don't really have any other way except maybe to use some calculator help and some approximation process in this. Let's suppose that our function is the function y equals 3 to the x. And we want to know this. And we want to approximate it using this definition of derivative. So is it okay that I put in 0 everywhere there's an a? Right? We want to know the f prime at 0. We have a definition for the f prime at a. So here's what we have by definition. In our problem, we want a, the specific x value that we're handed, we want to be 0. So we want the f prime of 0. So what is the f of 0 plus h? Well, 0 plus h is just h. What's the function with h replaced for the variable? 3 to the h minus the function with 0 replaced for the variable. 3 to the 0, right, which is 1. Now this is what we're going to have to approximate. Okay, we don't have any algebraic little trick to avoid. I mean, if we put in 0 in the top, what do we get? 1 minus 1, which is 0. And if we put in 0 in the bottom, we get 0. So we get 0 over 0. So we're not going to be able to do anything with this. So this is where we want to approximate. So let's let h be, I don't know, some small value, 0.01. What is 3 to the 0.01 minus 1 all over 0.01? Need some help here. A little more than 1?
Yeah.
Like 1.1.
1.1?
Yeah.
Okay, let's keep going with that process because we're supposed to let h approach 0, right? So if h is 0.001, about 1.5. No, not yet. 1.09. I was thinking the answer was going to be 1.04. Maybe I was
I have 1.09.
1.09. Okay, let's do this as our last value that we're plugging in. It's still not 0 yet, but it's pretty darn close to 0. Right, we're supposed to be letting h get close to 0, which I think is happening here. Anybody? 1.098. 098. Now, if we continue this process of letting h get smaller and smaller and smaller, we would actually converge on the value natural log of 3. Somebody punch that in your calculator. What's the natural log of 3?
1.09.
1.0986. So that's the value we're getting closer to, which you're not supposed to know that at this point in time, but I'll just tell you that that's where we're headed with this decimal. So we were pretty close here, very close, actually all along the way because we started with pretty small values of h. So is that what we wanted it to be? Is that the f prime of 0? That was it, right? Weren't we simplifying this thing right here? That was our answer. And we did that. We took the limit, kind of. I mean, we did it by approximating and letting h approach smaller and smaller values. So as h was approaching 0, we've got this thing to be approximately. So if we don't have an algebraic way to substitute, then just plug in values for h that get smaller and smaller and smaller and see what you get. Which at this point in time, we don't have any other way to handle 3 to the h minus 1 all over h as h approaches 0. So what did we just find? We just found a derivative at 0, but keep in mind what that is. That's the slope of the tangent line to that function. In fact, let's do this. So our original function was this. We wanted the f prime of 0. We just found it to be 1.098, roughly. So on this curve, y equals 3 to the x. Which looks something like that. Y equals 3 to the x, a little steeper than y equals 2 to the x, and in fact a little steeper than y equals e to the x. We just found the derivative at 0, which should be the slope of the tangent line. So what should the slope of that line be approximately? 1.098, right? I don't know how accurate my diagram is, but that's a rough picture, anyway, of what it is we just found. Yes?
So if we do this equation by shortcut, you find the derivative, so it's x into 3 to the power x minus 1.
No, it's not. This has a different, when the variable is in the exponent position, that shortcut that some of you know and are using to this point in time won't work. Yeah, in fact, when we get to a shortcut on this particular problem, we're kind of forced to evaluate that, except we're going to get a little better answer than 1.098. We're going to actually show that that's very, very close to, and in fact approaching, the natural log of 3. Yeah, the other shortcut will not work because the variable is in the exponent position. Okay, the third piece that I've already mentioned that I have a hard time kind of not mentioning is that the derivative is the slope of the tangent is the instantaneous rate of change. At a certain x value. So at the x value a. And I believe that's exactly the way it's stated. Let me find that other sheet here. So this second piece right here. The derivative f prime of a is the instantaneous rate of change of the function with respect to x. Now I didn't say that. With respect to x means kind of in terms of x. That's what it means. When x is equal to a. So a quick summary of today is, now we've got another example or two I want us to look at, but the derivative is the slope of the tangent is the instantaneous rate of change. All three of those. When you think of one, you ought to think of the other two. It's hard to separate them. This type of instantaneous rate of change we've already worked with a little bit. We've done, I know, one example in here. So let's kind of pick up on that. If we start with a position function, so the s of t, and before I think we used called it a distance or a height or a position function. So in this particular problem, it's a position function where s of t is in some linear distance, some location type unit, where it is in reference to some starting point, and then the t can be some unit of time. So when we have a s of t, a position function, let me give our position function here. Now the reason I chose this example, it's similar to the one in the book. It's not exactly the same as the one in the book, but I want us to look at one that has a rational function set up. Polynomials are pretty simple because it's just algebra and a lot of terms are dropping out and that kind of thing. Polynomials are a lot of times kind of overly simplified. Sometimes we have to do battle with these. Let's say that we want to find the instantaneous rate of change, and I'll just leave it at t, so for some arbitrary t value. Well, we decided that if we are given a distance or height or position function, and we find the instantaneous rate of change, in fact, if I state it that way, it's probably a giveaway. What's the instantaneous rate of change of distance with respect to time?
Velocity.
That's velocity. And then we can use that once we get a velocity function for this, which is really just the first derivative. So that's another thing I have a hard time with. I just called it the first derivative. Now when I do that, that leads you to believe that there are other derivatives, right? Second derivative, third derivative, fourth derivative, which there are. If you take the derivative of the derivative, you'll get a second derivative. And if you take that second derivative and take another derivative, you'll get a third derivative. Now, not all those have exactly the meaning that we would like them to have, but there are some types of problems that will need a third, fourth, fifth, seventh, 11th derivative. Most of the time, we'll need a first derivative and a second derivative for our purposes.
You can find the acceleration with that.
Right, acceleration is the second derivative here because it'd be an instantaneous rate of change of velocity with respect to time. And then we could take that result. Now we've got a battle here ahead of us to get the result, but once we get the derivative, which is this new function, this velocity function, we can plug in 2 into the variable position, and that'll give us the velocity at the 2-second mark or the 2-hour mark or whatever units we happen to be using in this problem. So let's find the derivative of the position function. So that ought to be the s of t plus h minus the s of t all over h as h approaches 0, right? Wonderful planning there on my part. To squeeze that little limit in there as h approaches 0. That's important. Okay, what is this function with a t plus h put in for every t? Well, there's our function.
H over 1 plus
T plus h
2 times
over
1 plus 2 times T plus H.
1 plus 2 times the quantity t plus h. Is that okay? So we're going back to our original position function. Everywhere we see a t, we're going to plug in a t plus h. So that's a nasty looking fraction. From that, we'll subtract the s of t. That's the way it's handed to us, is an s of t, so we just rewrite that. All over h as h approaches 0. So what's ahead of us here? What do we have to do? Common denominator. We're going to try to subtract 2 fractions in the numerator. And we can't add or subtract fractions without like denominators, which kind of looks bad. That's why I wanted to do one of these in class. So what do I need to multiply each fraction by so as to get a common denominator? Let me ask another question first. That's probably too quick. What is the common denominator? The product of the 2 denominators. Okay, so this one needs a 1 plus 2t, right? Here and also here. Well, that's a mess. And what does the other fraction need to be multiplied by? The other denominator. Is that okay? So what did we just multiply each fraction by? 1, right? Each fraction got multiplied by 1. This version of 1 was 1 plus 2t over itself, and this version of 1 was 1 plus 2 times the quantity t plus h over itself. So we're not changing the value of anything. Now, all of that needs to be divided by h. How can we accomplish the same purpose? Times 1 over h. Now, I'm out of room out here on the right. So I'll bring that here. So that's dividing everything by h. We're multiplying it by 1 over h. Everybody all right with that? And I picked an example that wasn't a real simple, obvious example so we could do battle with algebra because that happens quite a bit. T plus h times 1 plus 2t. Let's just multiply it out. What do we get there?
2t squared plus h plus 2.
Okay, now I'm going to keep that as this numerator. The denominator is the common denominator, right? They both have that denominator now, so I'm just going to put the numerators together over that common denominator. Everything that follows gets subtracted according to that. What gets subtracted here? T.
Plus 2t squared. Well, minus 2t. No, plus 2t.
Okay, I've got the parentheses, so everything's going to get subtracted. So t times 1, t times 2t, right?
Plus 2t.
And then 2h times t. So that gets multiplied by 1 over h as h approaches 0.
We're left with h over the denominator.
Okay, now without distributing, let's see what's I don't want to write all this down again, it's already cumbersome enough. Any terms that we're going to lose?
T, 2t
T
squared,
minus t drops out.
2t squared,
Okay, 2t squared minus 2t squared, they drop out.
2th.
2th minus 2th. That helps the cause, doesn't it? So what are we left with in the numerator? H? And this gets multiplied by 1 over h, which also is going to help the cause. So we can cancel h over itself as long as h is not 0, which it isn't. I'm going to go ahead and distribute that. You don't have to. Now what happens, by the way, it's okay, right, to let h approach 0 or some small number very, very, very close to 0. So what happens to this term? Disappears? That term approaches 0. So are the two factors in the denominator exactly the same? Exactly the same. So that ought to be the derivative of our original s function at some arbitrary value t. Is that okay? And if that's the derivative of s, that is also what?
Tangent.
Slope of the tangent. What else?
The rate of change.
Instantaneous rate of change. And what do we know? What else do we call the instantaneous rate of change of an s function with respect to t?
Velocity.
Velocity. So we've just found a velocity function. We started with a position function, we took its derivative, we now have a velocity function. Now back up to this page. That's a pretty easy question now, right? The velocity at the 2-second mark, at that instant, what is the speed of this object that is being described as the original s of t in the position function? So we would plug in t equals 2, right? What's that look like? What is the velocity at the 2-second mark? 1 over 25? And whatever the units are, that'd be the linear distance unit divided by the unit of time. So I didn't establish the units here, so. But it can be kind of ugly algebraically, which is why I chose that example. Questions before I move that one? Okay. I'm not going to do a specific example here. I just want to mention some terminology. Let's suppose that you're given a cost function. So you're given some C of X, it's the cost of manufacturing X item. Okay, it might be in hundreds of dollars or thousands of dollars or millions of dollars, it's cost. So when we have ordered pairs, this would be number of items and this would be the cost for manufacturing that number of items. So that's what our ordered pairs look like. You'll see this term, I think I've mentioned it once in here, marginal cost. Marginal cost, they're talking about cost on the margin, so if we were to look at it at a certain point and manufacture or produce or sell one more unit, what would be the cost involved with the manufacture of one more unit? So marginal cost is the derivative of the cost. That's the instantaneous rate of change of cost with respect to whatever the variable is. And we don't know the function here, so we can't fill this in, but we can fill in the units. What would the units look like for marginal cost in this particular description? Cost per
Unit.
item, right? Cost per item. So it's kind of at some instant in time you're going to freeze the situation and say, gosh, if we made one more item or one more 1,000 items, how much cost is it involved for us on the margin there? What's the marginal cost involved? So if you see the word marginal, marginal cost, marginal revenue, or marginal profit, they're talking about the instantaneous rate of change. First derivative. If you have a population problem, and maybe it's in the ordered pair where T is in years, and the P of T is in, let's just say it's number of people. So if that's our ordered pairs, and we have this function, this P of T population function, we want an instantaneous rate of change of population. So that could give us the growth rate, right? Instantaneous rate of change of population. If the population is in fact growing, that would give you the growth rate for the population. So again, we don't know the function, so we don't know what to put in this box here. But what would the units be?
Per year.
People per year, right? Does that sound like a growth rate possibly to you? Population growth rate. So you're asked to do those kinds of things in some of the exercises at the end of this problem set. We've got about 3 or 4 minutes, and I know we've got some problems that I need to clean up. Maybe I can get one of those out of the way. If you've got a question on a problem, let's dig back into 2.5 possibly, or 2.6. I think we're at 2.5 as far as cleaning up homework questions. Maybe we can get one problem answered here. So I'm looking at page 139 and 140. Section 2.5. Did we clean up all the 2.4 questions? I think we have, but tell me if I'm wrong there. Don't hesitate. I get told I'm wrong several times a day by the people that live in my own home with me, so I can handle it.
16 on 2.4.
2.4, we do have one?
16.
16? All right, let's do that one. That's about all we have time for, I believe. Explain why the function is discontinuous at the given number. Sketch the graph. Did we do 16 in here? Did we go all the way through it and sketch it? I thought we sketched that already. Now here's a quick indicator. I think we've done 16. Check back in your notes and see if you have it. I'm pretty sure we did. Because we graphed part of a parabola and part of a line. But here's a giveaway when you see a problem like 16. Right? Are you finding it? I think we did it. But
Yeah, we did.
if you just want to examine it real quickly, we're concerned about it being continuous at x equals 1. Shouldn't both pieces of this split domain function be the same number at 1? In other words, you could have a picture that came up here and had an open circle as long as the other piece, whatever it looked like, included that open circle, right? Kind of that removable discontinuity. So if you take the discontinuity or the open circle from one piece and fill it in with the other piece, it's probably going to be continuous. Now, is that the case here? What do we get here when x is equal to 1?
2.
We get 2? Be nice if we could see that too. And what do we get here when x is equal to 1?
3.
Does that tell you, give you a pretty good clue that it's not going to be continuous? Probably got a situation where we're coming down to different values. If we're coming down to the same value, it's got a good chance of being continuous. But without doing all the graphing, you can probably say that the limit is not going to be the same from the left as it is from the right. One of them's headed toward 2, and the other one's headed toward 3. So it's probably going to be discontinuous. All right, well, we can stop with that. Let me put some problems up from this new section, page 155, that I'd like for you to take a look at. Now, the problems, as we go through here, are getting fewer because the quantity of time involved to do the problems is more. So I'm trying to be somewhat sensitive of that relationship. Not that all of them take a long time, but some of them do. Now, there are a couple problems here that you can look at it and basically jot down an answer, but others are going to take you some time.
And our 2.6 is due tomorrow?
Yes. So that'll conclude lesson 20. I'll see you tomorrow.